welcome. In this lecture, I'm going to go through how we can use the tangent line to approximate functions. So let's kind of look at the setup first of like the picture. So suppose we're in a setting where we have, the first thing that we have is that we have f is a continuous function. So f is a continuous f is a continuous function. And the other thing that we need to be true is that x is going to be close to a. So x is close to some specific value a. Okay, so suppose that we're in this setting. Then we have this kind of picture going on. So we have, oops. I thought I picked up the green. So we have, so this is our y-axis and our x-axis. And we have the graph of some function. So we have y equals f of x. Maybe this is y equals f of x. Oops. Can I fit in y here? No. So we have y equals f of x. Okay, and then we have, so we have these two values. So we have this value a. I'm going to look at the tangent line at a. Okay. And I'm also going to draw the tangent line in green just because there's only so many colors we have that work here. So we're going to draw the tangent line here. Okay. And we know the equation for the tangent line. I'm going to write it in a slightly different form. I know you've seen it written in a slightly different form. It's the same. You can just manipulate it to look this way. So we get that y equals L of x equals f of a plus, and then we have f prime of a, and then we have x minus a. Okay, and so we're going to look at, and right at this point here, what is this point here? This is good to have everything labeled here so that we know exactly what we're doing. So this is a and then f of a. Okay. Now what we're interested in is to figure out the value of f of x, or at least to approximate it. So let's say this other value x is here. Okay. Then I can kind of put this in, right? So, you know, in theory, I love to have, right, I'd love to be able to go up and know exactly what this value is. Okay. I mean, all that I really know is that it's x f of x. F of x. The problem is that I don't necessarily know what f of x is. It might be very difficult to compute. My function may not be easy to compute at that point, but maybe it's easy to compute at a. And so I was able to compute that and its derivative so I could create this equation for the tangent line. And what I can kind of see is that hopefully if the tangent line, like if I'm close enough here, the tangent line should be, it's going to be able to approximate. And I could get here, this point, so I have x and then L of x, and these should be really close, right? And the hope is that these 2 points, I know I've already used a there, but I'm going to use this anyway. So hopefully close, hopefully this distance is small. Okay, because if that distance is small, that would mean this f of x and this L of x are really close. So this gives me a good approximation for what the output of f would actually be at x. Okay, so the tangent line equation, so from over here, right, so this is really the tangent line equation, but let's just kind of put everything in the same place. So we have the tangent line equation. Written in this form. We've written it in other forms. We haven't written it in this form explicitly, and so let's just kind of write it in this form. Is going to be y equals f of a, sorry, f of a plus, and then we have f prime of a times x minus a. Okay, so this gives us approximation. So this gives an approximation. And the approximation that we're going to get is going to be that f of x is going to be approximately equal to, and it's going to be f of, and we're just going to use this from off here. So f of a plus f prime of a times x. This x is this x here, so I do need to actually stick that in. This is where I stick it in to get the approximation. Okay, so I have to stick both a and x in to get this. First, I'm going to stick a into f. I need to evaluate the derivative and then stick in a. And then I stick in this difference here, this x minus a. So that's actually coming from, just to kind of illustrate on here, that's actually coming from here, right? This distance here is actually x minus a. Okay, so then this, so what is this called? And this is called, so this has maybe two names here. So this is called the linear approximation or tangent line approximation. So linear approximation. So what this equation right above is called. So this is called the linear approximation or tangent line approximation. So or tangent line approximation. Okay, and then we have this other formula. So we have this formula L of x equals f of a, plus this formula up here, plus f prime of a times x minus a, right? And where you're inputting, right, this is an equation, or this is a function. This is the function L of x, and this is the variable that's inputted. Everything else, so this would be the linear approximation, or the linearization, sorry, of f at a. So this is called, right, so it depends on a, and that's kind of a key point. Okay, so this is called the linearization of f at a. So this is called the linearization of f, right? You needed a function, so linearization of f. But you also had to say where it was at. So the linearization, just like the tangent line is different at different points, the linearization of f is going to be different at different points. So at a particular point A, you get the linearization of f at A. Okay, so what do we do here? We're wanting to approximate the value of a function at a point. And we're hoping that there's a nearby point where we're able to evaluate the function there, as well as the derivative there, because we're going to need that. And then we're going to say, well, if this is close enough, then hopefully the tangent line is still pretty close to the function, and I can use the equation for the tangent line to approximate my value for f, instead of putting it into the function. Okay, and then there's just some terminology here. So that was the tangent line equation. We already know this. This gives us approximation, which is called the linear approximation or the tangent line approximation. And this function, right, which is really the function that kind of gives you the tangent line, is the linearization of f at a. You would get a different linearization, so a different function, a different a, just like you get a different tangent line at a different a. Okay? Just saw that I missed that A being red. Okay, so hope that made some sense, and I will see you in the next lecture.